guys have done a really good job with making
Are her
lemonade.
birds still in good health?
You didn't have lemons. You
Yes.
had, building blocks. Really made a
Thanks.
great result. I think maybe what I was going to say is I'm just waiting. I'm just waiting for Neowise. I hope you guys didn't play. I'm on the tour.
I hope we do good.
I
really
make the
nice.
comment that we spent 10 years getting a house in Spectra, and you guys will blow us out of the water in a week. It's great. So you get I think that's really what it is. I was going to tell you an aside. Eventually we will blow it out of the water.
It's really exciting to get
Yeah.
one more order of magnitude.
It is. It's
Especially
great.
when there's so many objects out there.
It's fun to watch. It's fun and it's painful to watch. But no more power to it. We're waiting for the magic time.
Good afternoon. Welcome to the day 3 of the press briefings at the 47th annual DPS meeting here at National Harbor. My name is Dr. Vishnu Reddy. I'm the press officer for the DPS. Today we have a very exciting press conference. To my far right is Dr. Carrie Nugent from Caltech and IPAC. She's going to give some insights into the Neowise mission, how the results are going after 1 year. Next you have Dr. Rick Binzel from MIT. He's going to talk about the source regions of potentially hazardous asteroids in the main belt. Then we have Dr. Diana Blaney from NASA JPL. She is going to talk about ChemCam on the MSL rover on Mars. Then we have Dr. Carrie Anderson. She's at NASA Goddard, and she's going to talk about Titan. And finally, we have Giada Arney from University of Washington, and she's going to talk about organic hazes on Earth-like exoplanets. And with that, I'll call upon Carrie to take over.
Thanks, Vishnu. So today, I'd like to tell you about the Neowise mission. Neowise is an asteroid hunter. Its goal is to discover and characterize asteroids. In the first year of the reactivation mission, Neowise measured the sizes of almost 8,000 asteroids. Neowise is an infrared telescope that orbits the Earth. It was originally an astrophysics mission designed to study the coldest stars and the most luminous galaxies. WISE rolled off the assembly line with all the newest technology and all the bells and whistles. It was able to snap an infrared image of the sky every 11 seconds from its sun-synchronous orbit, shown in the animation. It images the entire sky every 6 months, and after a highly successful initial mission, it was placed into hibernation. In 2013, it was revived with a new goal to find and study asteroids. We on the team like to think of Neowise as a first car. The new car's smell is long since faded, and it's got 880 million miles on the odometer, but it still runs great. Neowise has taught us how powerful infrared space telescopes are for studying asteroids. So over the course of its mission, Neowise has seen over 158,000 asteroids and comets, and it's discovered more than 35,000 asteroids. Neowise does not see resolved asteroids, we just see points of light. So this is a pretty colorized photo of a main belt asteroid. The asteroid in this image is large, about 620 meters across, but it is also very far away, about 300 million miles. So it's very small in Neowise's images. For a sense of scale, 620 meters is roughly the width of Disneyland. So the asteroid in the image is about a Disneyland wide, a Disneyland tall, and a Disneyland deep. And to follow through with the analogy, this particular asteroid is about 750 Disneylands away from Earth. So as you can see, we can't measure the size directly from how big the asteroids look on our images. We need to use another method to measure the size. That method is thermal modeling, and it is very powerful. So if you look at the top half of this graphic, you can see you can have a hard time distinguishing between a very small, very reflective asteroid and a very big, very dark asteroid. They both emit the same amount of light. However, if you look at asteroids in the infrared, you're looking at the amount of heat emitted from the asteroid. So the brightness you see in the infrared corresponds directly with how big the asteroid is. So if you have a nice computer model that can simulate how hot the asteroid is and how far away it is from your observer, you can back out the size. And you can see once you have a measured size, you can compare that to the visible measurements to get an albedo. And an albedo is the percentage of light reflected. So at that point, you can see whether it's reflecting a lot of light or absorbing, or if it's very dark. So that's what the team did for the first year of the reactivation mission. We measured the sizes and albedos of almost 8,000 asteroids, including 201 near-Earth asteroids. I just have one plot for you guys. This is a plot of diameter versus albedo. The teal circles are objects that we observed and measured the sizes and albedos for, and the black squares are objects that Neowise discovered. So you can see that Neowise discoveries all cluster in that bottom corner there. We're finding large, dark asteroids. When I say large, I mean objects that are hundreds of meters across to about 1 kilometer. And when I say dark, I mean reflecting less than 10% of light. In fact, Neowise can see objects that are as dark as printer ink, so incredibly dark. And you can see from this that Neowise is very complementary to NASA's existing ground-based assets. All those ground-based assets are looking at visible light, and so they're biased towards the very bright objects, and we're scooping up these large dark objects that's hard for them to see. So although Neowise has been a reliable workhorse operating long past its planned lifetime, the mission will eventually come to an end. Neowise's orbit is changing, and sometime in 2017, engineers estimate that it will be in too much sunlight to function. However, the team has its eye on a new space telescope, and this one has a little bit more muscle under the hood. The principal investigator of Neowise, Dr. Amy Meinzer, led a proposal for an asteroid hunting spacecraft, the Near-Earth Object Camera, or Neocam. Unlike Neowise, Neocam is specifically designed to hunt asteroids. Neocam is one of the 5 Discovery-class proposals funded for further study this year by NASA. Neowise has taught us how powerful infrared space telescopes are for finding and characterizing asteroids, and we can't wait to see what Neocam will discover. Thank you.
I'm going to add a slide to my talk if you'd like to go next. Okay. I just thought of a great illustration to add to my talk. To resubmit it back to the back of the
Okay. So how do I set up? So yeah, go to the Blaney talk.
well done.
All right. So I'm going to bring you some results from the Curiosity rover, which has been exploring Mars now for over 3 years. The focus of this talk, it's kind of hard to come up with 7 minutes worth of stuff to talk. So I'm going to focus on a place we've recently been exploring called Garden City Vein Complex. And I really would like to highlight the work of 2 students who are on this project. Marion and Sean, who's been doing a lot of work with the ChemCam diagenesis, and Rachel Cognac, who's been doing the mapping with the MOLI and MassCam images of the vein intersections. So Garden City is this vein complex at the base of this cap rock you see. You can see the scale bars that the cap rocks are we're talking things that are in the meters scale part, and the vein complex we're talking about is this network about midway through the page of light and dark raised materials. This is in the upper portion of the Pahrump section of the Murray Formation, and the vein complex emerges from fine-grained mudstones. Previously, Curiosity has found evidence that these base levels of Mount Shark were deposited in lakes and rivers, and these wet conditions recorded by the Garden City veins are from a later area than those things. Basically, the mud deposited in the lakes and rivers had to be solidified prior to their formation of these veins. The veins are generally seen on Earth, and including some of the types that we've seen here on Mars. And the chemistry of the vein formation is related to fluid interactions with rocks. Here at Garden City, there's 3 broad classifications of veins based on morphology and texture. There's the first class, which are thin, platy, fracture-filled material, very fine-grained, and low albedo. So they're the dark stuff labeled with 1. The next type of veins are thicker, dark veins that frame these large fractures. And then moving up through those things are light-toned materials that frequently go through the dark veins, and so look like they were the latest thing to have happen at this location. The timing of this was really great with respect to ChemCam. ChemCam provides the ability to make compositional measurements at the sub-millimeter layer. So we're able to get into these veins and really see what the chemistry is on a location by location measure. ChemCam uses a technique known as uses a laser to basically plasmatize the rock and then look at that light back through a spectrometer to tell what elements are there. This is the first LIBS instrument that has been used in geochemistry and in any planetary missions, and it's also even a relatively new technique to be used on the Earth. And one of the things that was really exciting about the Garden City is the data came in right after we had completed a really extensive upgrade to our data analysis toolkit. We were lucky, we saw a lot more extreme compositions that we were expecting to see on Mars, so we expanded our spectral library of rock analogs to include more end-member, and we added some new computational techniques. And this allowed us to develop a new way to calibrate ChemCam, which to deal with more extreme compositions and more accuracy and precision in the analysis. So looking at the ChemCam things, the dark material, your initial thing might be that, oh, they're all dark, they're all the same. But when you actually look at the chemistry, there's a lot of variability in the dark material. The thin fracture fill material has 2 different compositions. They're dominated by higher iron, and one set has higher potassium than others. The scale bars are kind of show you really how the elements change between those 2 things. And these are images with the LIBS RMI, and basically each little square is the size of a LIBS analysis on these measurements. The darker veins were actually had some really stark chemical differences. When you look at the pictures and you look at the images, they look very, very similar, but the chemistries are very different. They probably formed from different fluids. The figure on the left actually has a large amount of calcium fluorine in it, as well as iron. And the one on the right is dominated by more magnesium and iron and stuff. I'm going to go really fast because I'm going behind. The white veins are calcium sulfate and all look very similar. But texturally, the white veins which came in left have different textures. Some that are due to ataxial crystal growth, which means the fracture is filled by the grains flowing in them, and others that look like they were high pressure injections of fluids. You can see the injections, and you can also see dark material torn up here. So in conclusion, the texture and chemistry indicate that a variety of fluids move through the rocks at different times. This happened after the lake sediments had solidified, and the fluids contained iron, calcium fluorine, and magnesium, and they formed a complex nature of day. These veins really extend how long the water was around, and the fact that you had time to involve these different fluids mean that there was complex chemistry going on at Gale even after the lake sediments were posited. And this may have implications for how long water was available to support habitable environments, in addition providing widely different chemical environments to assess for habitability. Thank you.
Thank you very much. I'm Richard Binzel from MIT, astronomer at MIT. I want to thank Diana for stepping in. As I was sitting there and hearing the first talk, I thought of the perfect illustration for why, for the work we're doing. So it's just like a professor to come up with the right answer at the last minute. So my work is trying to understand where the near-Earth asteroids come from. These are the asteroids that present us with opportunity for exploration and also present, over long timescales, hazards to the Earth. And this is a diagram of a few thousand of the known near-Earth asteroids. This looks like a kid's spirograph diagram. And you can see the outer circle is the orbit of Jupiter. Moving inward is the orbit of Mars, and then there's the orbit of Earth. And you see that the Earth is constantly intersected by the orbits, literally of thousands of near-Earth asteroids. The good news is that space is three-dimensional, and that the Earth is very small in this diagram, and the asteroids are even smaller. So the timescales over which the Earth is hit by anything of consequence is hundreds of thousands to millions of years. So our goal here is to try to understand, where does this bizarre mix of asteroids come from? And for a variety of reasons, we think they come from the main belt. And the reason for that, if you'll allow me, let's see, can I click there? If you'll allow me, and with some apology, what we do is we measure how these objects, asteroids that are near the Earth and asteroids in the main belt, we measure how these objects reflect sunlight. I mean, we look for ways in which the surfaces of these objects absorb sunlight and tell us about their compositions. So these are near-infrared spectra. And I don't want to spend time on that other than to say we have a measurement technique. And there's been this fantastic workhorse facility for many years. It's the Infrared Telescope Facility in Mauna Kea, Hawaii, operated by NASA. And it's an incredible resource for the community, and it's one of the workhorses for understanding the whole issue of asteroids and potential hazards that they pose. All right, so I'm using a technique where we make these spectral measurements of asteroids and combine them what theorists think about in terms of trying to figure out, how do you get an orbit out of the asteroid belt into one. The asteroid belt is the stable region between Mars and Jupiter, and why is it some asteroids leave the main belt and come intersecting with the Earth? And the dynamical models look at the orbit of an asteroid that is near the Earth and try to backtrack where it came from. But it's not an easy problem, because the planets scatter. Once an asteroid is near the Earth or near Mars, the planets will scatter it, and you lose track of where it came from. So it's a very tricky problem. And we're trying to decode both the compositional color information we get from the asteroids and this orbit information, see if we can make a coherent picture. And the models that tell us where a near-Earth asteroid come from look like this. This is a model by Bill Botke of the Southwest Research Institute in Boulder. And there's 4 jargonish labels at the bottom, to which I apologize for. But coming from the inner solar system and moving out, we have objects that come from the Mars crossing region. In other words, they get scattered in because they interact with Mars. And then there's these resonances with other planets, ways that the asteroids will interact with other planets that we call resonances. And they have great names like Nu 6, a Greek letter Nu, number 6, 3 to 1, outer belt and Jupiter family comets. And this is a set of probabilities for objects coming from each of these locations. And the sum of those probabilities is 1, because an object that's near the Earth had to come from someplace, because they don't live very long. They don't live forever once they're near the Earth. And so the short answer is we take a subset. We look at these asteroids in their reflected colors and try to figure out what kind of meteorite or what they're related to. And a short answer here is that asteroids that look very dark and very carbon rich, some of the most primitive material in the solar system, seem to be coming into near-Earth space from the farthest edges of the asteroid belt. And we call these in jargon the C-type asteroids. They're related to a kind of meteorite called carbonaceous chondrites. And we love to go sample these and measure these because of their early origins. And we see that the asteroids near the Earth that look like these meteorites and probably deliver these meteorites come from the farthest reaches of the asteroid belt. And asteroids come in all different varieties. The meteorites that we collect come in all different varieties. And on the lower right is just a diagram that, again, is these spectral measurements, just to try to at least visually illustrate we get different kind of compositions. And each of these labels has a different chemistry to it. And we see for the different chemistries, different regions in the asteroid belt where they're coming from, sort of how the bars along the top peak in different locations in the asteroid belt. And what this means is that we're seeing for different kinds of near-Earth asteroids and what we interpret for different kinds of meteorites, we are seeing very specific places in the main belt where they're coming from. And it's really interesting because the main belt has places where each of these kinds of compositions tend to be localized. And we're getting a match. So the news is we're getting a match for the near-Earth asteroids, the asteroids we see near the Earth. And when we try to deduce where they come from, they're coming from where they're supposed to. The things that look like the outer belt in the asteroid belt, and the near-Earth asteroids that look like things in the outer belt, when we do all the math, we get the answer that they came from the outer belt. So we've had this idea and we've figured out it would work this way, and when we finally get the data and can do the analysis for the first time, we're getting that answer. So that's the news there. The things that come closest to the Earth and are ever potentially hazardous to the Earth tend to come from the inner edge of the belt. That's simply because that's an easy place to sort of wander in and have kind of an Earth-like orbit in the same plane as the Earth. And so the things that usually show up in the newspaper will be things that have come in from the inner edge of the asteroid belt. It turns out that's the easiest place to get things that will come close to the Earth. So that's another idea that we had, that we figured that was how it worked, and our data show that. And we also are looking at where some of the objects that we're going to have sample returns come from. They tend to come from the inner belt. In other words, before they wandered into the space near the Earth, they were residing in the inner belt. But we find their cousins all the way out in the outer belt. So we have high confidence that we're ultimately sampling the outer belt. And the last thing I'll say is that we have groups of meteorites that form in these different classes, a class called Ordinarychondrites. They're 80% of all meteorites fall in this class of that we give these wonderful letters of H, L, and LL. And we didn't know where in the asteroid belt these all different kinds of meteorites were coming from. And now we sort of have a map for the bulk of the meteorites in terms of different locations in the asteroid belt. So just to wrap up, this has been a detective mission of trying to combine telescopic data on the ground. We have data on 1,000 objects. It's taken us a decade to collect. And we're combining them with the best orbital models, and we're starting to get to see answers that confirm a lot of our notions, and even decoding where a lot of the samples in our collections are coming from. So thank you.
Good afternoon. Okay. All right, I'm Carrie Anderson. I'm from NASA Goddard Space Flight Center. Okay, so a little background here. All right, so back in 2012, the imager on Cassini detected for the first time a cloud hovering over Titan's south polar region, and it was observed to reside at a very high altitude, around about 300 kilometers. Now, this is a camera that picks up on reflected solar radiation, and later on it was found out from another instrument called VIMS that a major component of the ice composition consisted of HCN ice. And so if you look right, let me get this mouse to it, look right about, here's this cloud. And it's kind of hard to see from this view here, but what's nice about this is that you can see how sunlight near about 300 kilometers, which was very unexpected at that height, because that's near the very top of the stratosphere, it catches the top of that cloud, and that tells you the vertical extent of it. And so below it in altitude and at the nearby surrounding latitudes, it's in darkness. So now enters another instrument on Cassini called CIRS, the Composite Infrared Spectrometer, which does not see and reflected solar radiation, rather thermal infrared radiation. And so what that means is we can come in with CIRS and we can peer into the polar darkness deeper into the stratosphere and observe the cloud activity that is going on that the other imagers on Cassini cannot see. And so what we have found from a recent flyby, T112 back in July, is that this ISS cloud near 300 kilometers turns out to just be the tip of a more extensive stratospheric ice cloud system. Okay, so now what I want to illustrate here is on these pink circles that scan all the way down, this is to illustrate, it's a schematic that illustrates the type of a limb scan we have in the far infrared. And this is how we do this type of limb scan to retrieve the vertical profiles of the particulates in Titan's stratosphere, the aerosol and the stratospheric ices. And so in the far infrared, we have a circular field of view, and what we do is we scan very slowly down Titan's limb, and these fields of view overlap significantly, and this is how we're able to build up a very dense network of spectra. And over here on the right, for one given wave number, it's at 200 inverse centimeters for this example, which is 50 microns, I'm showing you what this type of scan looks like, is intensity, whoops, don't look at that yet. Okay, well, there we go. Let's go back to this for a second. Okay, so the point here, I'm used to a Mac. Okay, the point here is that when you scan down on Titan's limb, this is for 85 north during mid-northern winter. This is the T4 encounter, which was March 2005. So when you scan down on Titan's limb, you're riding on zero intensity, very low into the stratosphere, until you get very deep to pretty much the mid-lower stratosphere, and the intensity starts to increase. And that's because you're finally picking up on signal from the aerosol, and that's why the intensity increases, and there you go. And that's what we tend to see. So now, when we saw from T112 at 75 and 79 south, this example is 75 south, we saw something very different. And in the 10 years I've been with the team, we have never seen something like this. Here you go in pink. You start to go down, boom, bump in intensity, and then we continue as normal. Well, there's our new cloud detection. Stood out, I almost fell out of my chair in my office. I really did. I couldn't believe it. Wow, what an increase in signal. And so normally it's very low intensity because CIRS is this is a part of the spectrum where we have excellent signal to noise. We're looking along on the limb, very long path lengths. We're integrating, we're picking up signal. And like we have a very dense network of points of scans here, so we have excellent spatial resolution. And so this was really neat to see. And so for comparison, this is where the ISS cloud is located in height. And so we're much further down to the ISS cloud in altitude. And you can see we don't see any signal from it. That doesn't mean the ISS cloud is not around right now in 2015. We're just not picking up on opacity from it. But it's probably gone into darkness anyway. And so we're just not seeing it if it's there. So we're much further down in altitude. But one other thing from during northern winter, anytime during northern winter, all the stratospheric ice clouds we saw were much deeper in the stratosphere, well below 150 kilometers. So we're seeing something much higher up, and this is a function of temperature and vapor abundance. That's why the clouds are higher, okay? All right, so the spectral dependence tells us something about the cloud composition. So what I'm showing here, you're looking at a figure, it's a plot, of relative opacity as a function of wave number. Now in the far infrared, nitrile ices have a lot of emission features, or lattice features, that overlap. And so we pick up on those. And so the white curve here just represents what the northern winter cloud system looked like. And this is what we discovered in Titan's stratosphere to exist. It peaks at 160 centimeters. It's very broad, and it turns out to be, from thin film measurements in the laboratory, to be a composite ice dominated by a blend of HCN and HC3N, which is cyanoacetylene. There's probably some other nitriles in there as well, but that's the dominant blend. But now, from preliminary work we just did, I retrieved this just a few days ago, you can see in the yellow curve that the spectral dependence is very different, and that points to a different chemical composition. And so we think it's still mainly due to nitrolysis, but relative abundances have changed. And one thing to point out is over here on the left, peaking at about 100 inverse centimeters, we're picking up an isolated signal, and we think that may be due to the lattice mode of cyanoacetylene, or HC3N. But if you look over here, between 150 and 250 inverse centimeters, that's where the new feature, the width of the new feature spans, and we think maybe this may be due to a blend of HCN and potentially cyanogen ice, and we haven't seen cyanogen ice in the stratosphere before. The laboratory work, thin films, will ultimately identify this. Okay, so what are the implications? Well, it appears that southern winter, which we're going into, will be there in 2017, is coming in pretty strong. And a lot of this, like I said, is a function of the temperatures and the large abundances of the trace organic vapors. We definitely know that the north-south atmospheric circulation pattern has reversed. The result of this is that you're bringing down fresh trace organic vapors down in different abundances than we've observed during northern winter. So that is happening, and they're coming down, okay? Now what happens when you get this increase in abundances of these different vapors coming down? There are more of them, they're coming down, and they're radiating. They radiate away thermal energy, and the result is they locally cool. So they really cool. When you get this cooling, this in turn leads to more clouds. More of these stratospheric clouds form, and they actually will start to cool as well, okay? And then lastly, the relative organic vapor abundance are rapidly changing as Titan heads into winter, just to say that one more time. And we see that manifested in the spectral dependence of the ices, because that reflects the relative abundance of the vapors that went into the formation. Okay, and to recap, once again, we have this new discovery from Sears. We see this cloud at altitudes considerably higher than we've ever seen it before at any time during northern winter. And like I said, we've been looking at this data for 10 years. The chemical composition is different than the northern winter cloud system that we discovered with Sears, that was peaking at 160 inverse centimeters, and now it's not. So it's a new cloud, different spectral peak. And we suspect that the new cloud is composed of nitrile ices, potentially a blend of HCN, cyanoacetylene, and cyanogen. And what's actually really neat about this, if you take a step back and you look at the big picture view, you've got your ISS cloud, and now we're looking at the larger picture of the south polar stratospheric cloud system, and Sears can see down, you can see the bulk now, like an iceberg. We can see the bulk of the south polar cloud system, which resides in altitude well below the reflecting clouds seen by ISS. Thank you.
Okay, hi everybody. I'm Giada Arney, a grad student at the University of Washington. I'm also part of the virtual Planetary laboratory, and I want to tell you a story in the next couple minutes about the most alien world that we have geochemical evidence for early in Earth's history. So let's first consider the exoplanet population. We've discovered a zoo of worlds out there that are very different from anything in our solar system, but we know there are also probably planets out there similar to Earth and have the capability of hosting life. So it's now a matter of finding these needles in the haystack and properly characterizing them. But when we look at Earth through time, we would see that Earth has looked very different at different epochs in its geological history. And so when we ask the question, what does an Earth-like planet look like? The answer to that question depends on the time period that we're thinking about. So what I'm studying here is Earth during the Archaean geologic period between about 3.8 and 2.5 billion years ago. Our planet was a very different place during the Archaean. For example, in our atmosphere, we had very little O2 and much more methane. If you were to go back to the Archaean, you would not be able to breathe the air because you would asphyxiate without an oxygen mask on. And just to give you a sense of how far deep we are into the geological record, this is about when the dinosaurs evolved on Earth. So we are way further back in geologic time. Now the point here that's important is the fact that there's much more methane in the Archaean atmosphere. We know from Saturn's moon Titan that when you have an atmosphere that's very, very rich in methane, complex chemical reactions can occur and transform that methane into something we call a hydrocarbon haze. So these haze particles form when that methane gets broken up by UV sunlight, and then the products of those reactions recombine into these hydrocarbon haze particles. And that's the reason why Titan is this orange color. I like to liken these hazes to the photochemical smogs that exist around industrialized cities. So the composition of smog is similar to the composition of these haze particles. Now, geochemical evidence suggests that in the later Archaean, when there was a lot of methane in Earth's atmosphere, there were times when our entire planet was enshrouded by one of these hydrocarbon hazes. So what we did in our study is we used computer models to simulate this haze and try to understand what it means for our planet's habitability, for our planet's climate, and for the planet's appearance. And an important point I want to make has to do with the source of the methane that produced the haze in the Archaean atmosphere. There's two ways you can produce methane. You can do it with biology, and you can do it with geology. And so if we compare the flux of methane on Earth from biology versus geology for modern-day Earth, we would see that the flux from biology vastly outweighs the geological flux. And we believe that this was also true in the Archaean, that the flux of methane from biological processes was much greater than those from geological processes. A cool thing that we found was that when we looked at where's my mouse? That's okay. When we looked at the plausible abiotic flux of methane for Earth-like planets and put that into our model, we were not able to form a haze in an Earth-like atmosphere. So for an Earth-like atmosphere that has a lot of CO2 in it, so when I say a lot of CO2, I don't mean a huge amount of CO2, but much more than Titan has, we find that we can't form a haze with only abiotic methane production rates that are consistent with estimates for Earth-like planets. So for Earth-like planets, the haze might indicate methane production by biology. And this haze is pretty cool because it's more easily detectable remotely than the methane itself. But there's a really important caveat here because planets are complicated. And Titan has these hazes too, but Titan's hazes are not formed by biology. So if we saw a hydrocarbon haze on an exoplanet, we would want to know whether that haze is on an Earth-like planet and produced by biology, or potentially produced by biology, or if it's on a Titan-like planet and not produced by biology. And these worlds could look very similar to a remote observing standpoint. So we'd want to be able to characterize the atmospheres that these hazes are formed in and understand the context that they exist in. And one of the important things that we can look for is the amount of CO2 in the atmosphere. So the haze formation is controlled by the ratio of methane to CO2. The more CO2 you have in your atmosphere, the greater the flux of methane needs to be in order to form the haze. So what we're finding is that at CO2 levels consistent with Earth-like conditions, you may need more methane flux to produce the haze than we would expect from abiotic processes alone. Another important thing these hazes do that's relevant to planetary habitability is they cool the planetary surfaces down by reflecting a lot of light back to space. However, we found that for the Archaean, even with the fainter young sun in the Archaean, CO2 levels that are consistent with what's allowed by geochemical constraints allowed for habitable conditions despite the haze's cooling effect. And then another consideration relevant to habitability is the fact that these hazes block a lot of UV radiation from reaching the surface. So the modern day Earth has an ozone layer in its atmosphere that blocks a lot of UV radiation. But in the Archaean, that was before the rise of the ozone layer, and the surface of the Earth would have received a sterilizing amount of UV photons. You would be killed if you went to Archaean Earth and stood out there without a spacesuit on that was very UV resistant. It turns out that these hazes are strong UV shields, not nearly as strong as ozone, but we find that the haze could block about 97% of the type of UV radiation that directly damages our DNA. So lastly, let's think about how would we test the hypothesis that hazy worlds might be out there in the exoplanet population. It turns out that these hazes have strong, remotely detectable spectral signatures, and one of the big picture things that they do is they change the color of the planet. So as you go from a planet with no haze, you can go from a pale blue dot, which is the canonical Earth-like type of planet, to a pale orange dot. So pale orange dots can be Earth-like planets too. And so in the future, when we're searching for these Earth-like exoplanets, we're going to want to make sure we can identify all of the Earth-like ones and not just the ones that look like Earth today. So in summary, haze-induced planetary cooling does not preclude habitable surface conditions. These hazes could act as a UV shield for early Earth and similar exoplanets. And the haze has strong observable consequences that you could see across interstellar distances. And if you can characterize the background atmosphere that the haze exists in, you might be able to argue that the haze could be a sign of life itself. Thanks.
All right, we'll open up for questions. Please raise your hand if you have a question.
It's for Diana. Emily Lochtawala from the Planetary Society. You've seen veins in a lot of different kinds of rocks. There's a lot more at Garden City. I'm wondering if you think that that there's different fluids in different rocks, if it's all the same fluid behaving differently in different rocks. How do you reconcile that?
So what I think has happened is, for instance, the calcium sulfate veins are relatively widespread, and I think that was a really regional signature, and then we've seen that pretty much everywhere we've been. What's happened at Garden City is, because there's such good preservation and we get the cross-cutting, that we're able to start pulling out some chemical signatures that we saw at different places into distinct fluids. And by looking at the cross-cutting relationships and the difference in chemistries, I think we have really strong evidence that they're distinct fluid events. There's a lot of diagenetic features that we've seen throughout the period, but in the main rock, these the chemical signatures and the veins are not as well preserved. One theory is because it's up against the cap rock, basically that acted as a little bit of barrier, so the fluids were able to form thicker veins, and so things that were at smaller spatial scales that are impacting the chemical signatures, now we can kind of see the end members. And so I think what we're looking to do is go back through the chemical data and see where else we had seen these signatures. We saw some fluorine signatures at other places on the things. I think there's some stuff with iron oxides also potentially going on in different places, and I think this kind of gives us a snapshot of distinct fluids that we can start looking for other places in the stratigraphy.
And if there's multiple distinct fluids, can you evolve the subsequent fluids from the earlier ones, or do they have to represent 3 distinct episodes of fluids?
There's a lot of work going on that. It's a really complex issue because it depends on what you're starting with, and then what gets moved. But you can't do it's very hard to do linear mixtures back and stuff, and it's trying to do the cation anion balance with the stuff is going to take us a long time to figure out. But the fact that these are happening at different times, and it's not a simple, I would say, dissolution from basaltic type type of easily recognized stuff. The calcium fluorine is a kind of a hard fluid to get, and then the variability within some of the other fluids is also hard to model in an integrated manner. We've got a lot of discussion going on, and people are working this issue really hard.
Hi, I'm Alexandra Witsey with Nature. My question is for Giada. I'm really taken with this concept of Archaean analogs. What about periods between 4 billion years ago and today? I mean, have you or others looked at modeling what an atmosphere might look like, 2 billion years ago, or as things evolved on Earth, and what that would look like?
Is this working? Yeah, there's definitely been work studying, say, the Proterozoic atmosphere and how that might appear. That's not the focus of my own work, but I have also simulated how Archean Earth would look like without a haze. So an atmosphere with a lot of methane and more CO2 than the modern day Earth, but haze free. And then an atmosphere with even more methane relative to CO2 and with this haze that forms. And what do they look like? So they're quite different from modern day Earth in the fact that they don't have oxygen in them and they don't have the ozone feature. So oxygen is sort of the canonical biosignature that we frequently think about. The cool thing about the Archean haze is that if we can regard it as a biosignature in certain contexts, it's a very strong spectral biosignature. It absorbs a lot of short wavelength radiation and produces a very broad spectral signature. That's the reason why it makes the planet look orange. And when the haze is in place, you basically can't see the Rayleigh scattering tail in the spectrum anymore. So it absorbs a lot of the blue photons away. Yeah.
Online questions?
Okay, we do have a number of questions from the online audience. We'll start with Irene Klotz from Reuters, who has some questions for Diana. She says, you mentioned that the ChemCam analysis of the mineral veins extends the period of time when water must have been available in this region of Mars. Can you be more specific about how much time water would have needed to be there to produce the chemical stew that you're finding? And would you say that this is the most chemically complex region that Curiosity has studied?
So it's really hard to do time because we don't know how far apart in time these different events occurred or really what was driving them. And I think as we get more information on what it's going to take to chemically evolve these fluids, we might be able to pin that down. But I can basically say that these fluids happened not only after the lake sediments were deposited, but also after the cap rock was deposited, because we see them going up through that section. So it's more of a relative stratigraphy, and so it's basically a time period between when the potential lakes, when the lakes dried up, and the current epoch. And as we try to figure out one of the interesting things to me is, for instance, the calcium sulfate and the high pressure. What drove the fluids? What are the processes involved? I think we can start then trying to figure out more time. I do think this has some of the most extreme chemistry that we've seen in a very localized area. There's been other places that we've seen very strong chemistry, but in this kind of meter square area, I don't think up until this point, I don't think we've seen anywhere with this much variability and this much really unexpected chemistry. Before we landed, if you had told me that we would be finding veins with these chemistries, I would have kind of raised my eyebrows a little bit. So.
Irene Klotz has a follow-up question for you, too. She asks, is there anything in this chemical analysis related to the preservation of organics?
That's not my area of expertise, so I don't want to really get too deeply into it. I do think that because veins have a good potential in general, because it's a fluid, and the crystallization to preserve things as inclusions. But the organic preservation has a lot of factors involving oxidation state and things like that I don't want to get kind of ahead of the people who are actually looking at that. I do know that people are looking for these veins themselves. Are not able to be drilled by the Curiosity rover. There's more veins that at a even larger scale than these that are ahead of us, and I know people are looking to try to see if there might be places where we could sample them and explore those hypotheses.
Okay, the next question comes from Kelly Beatty of Sky and Telescope. It's for Giada, Arney. First, he wants a clarification. He says he thinks you said that Earth's methane had to be generated, whereas Titan probably formed with lots of methane to begin with. Is that right?
So I don't study Titan, but I do know that the source of the methane on Titan is different from the source of methane on Earth, and that people are still working to understand where the methane is coming from on Titan. It's very unlikely to be biological. Could you repeat the question again? Sorry.
Well, yeah, he was asking. Well, he said he thought he heard you say that Earth's methane had to be generated, but Titan formed with lots of it to begin with.
Oh, okay, no, I didn't say that.
Okay.
But Earth's methane comes from geological processes and biological processes. It's just that the biological sources outweigh the geological processes.
Okay, that probably does answer then his question, which was, since methane is so common, could Earth not have sequestered a lot of it when it formed? What it sounds like you're saying is, sure, it could have, but by now the methane signature that Earth has been overwhelmed by the biogenic methane.
Yeah.
I know it's not your area, but okay.
Yeah.
All right. So the next question also for you from Leo Enright from Irish Television. Will you be going back over earlier data with this new toolkit? Oh wait, sorry, this is for Diana. Will you be going back over earlier data with this new toolkit, or is Garden City uniquely diverse?
We're going over the data with the new toolkit, and we're actually delivering data to the data center with this new calibration. Garden City is unique in terms of the large number of observations, but there are individual isolated observations that also had unusual chemistry that we're going to go back and be looking at again in detail. And we're also reworking, because of the improved accuracy and precision, we're also reworking some of the analysis to see if we can do a little more fine-tuning of some of our previous geologic interpretations and stuff. So yeah, so everyone's kind of diving into this, and we're trying to get this out to the entire science community as soon as possible.
Okay, and we have one last question here. This is from Daniel Fischer, a freelancer in Germany. This question is for Carrie Nugent, but I think Rick Binzel may want to address it too. Do the new near-Earth asteroid discoveries by Neowise change the impact risk statistics based on optical surveys in any significant way?
So there is a study by Binzel et al. That estimated the populations of near-Earth asteroids. That was published a while ago, but we haven't updated those statistics. However, we have found, we don't think we've found enough objects yet to change the conclusions of the previous Binzel et al. Study. Did you have a comment?
No, I'll add to that. Hi, Daniel. You have to remember, you probably well know that the WISE survey in measuring in the near infrared is much more sensitive to the darker objects, the lower albedo objects, which are harder to find with optical telescopes. And so it's very complementary in trying to address the overall population. So to my knowledge, and certainly defer to Carolyn, the statistics aren't in to see if our previous estimates of the low albedo or the dark objects is any different than our previous predictions. But it is indeed a very complementary process complementary discovery survey, and so your question is well posed, even if we don't have the answer.
And then I actually have a follow-up question for Rick Binzel myself. This is Rick Feinberg from the AAS. Are there any correlations? You found correlations between meteorite types and locations in the asteroid belt where you expected them to come. Do you have any correlations between some of the asteroids are large and dark. They're equally bright with some that are small and bright, or highly reflective. Are you being able to get any correlations at all between those surface properties and the spectral types that you're seeing? I mean, are large dark asteroids preferentially one type of asteroid, or do all the asteroids come in all these different sizes and reflectivities?
Well, that's a great question. So the different labels, the alphabet soup labels that we put on asteroids, tend to have specific albedos associated with them. So the C-type asteroids, I'm sorry to use the jargon, are usually dark and low albedo, and the S-type asteroids, the more stony asteroids, are brighter. So there are very specific correlations between albedo and types. And then that's something we're actively looking at to see if there's a size distribution associated with them. But off the top of my head, or at least what we've seen so far, we don't have the kind of correlations that you ask. But we're genuinely interested to see if at smaller sizes we tend to see a different flavor or a different proportion of objects at small sizes relative to large sizes, at least in terms of what's reaching the Earth.
And actually, while we were having this discussion, Kelly Beatty came up with a related question also for you, Rick. Do infrared spectra of near-Earth objects and potentially hazardous asteroids in particular tell us anything about their physical properties, such as porosity or cohesiveness, characteristics that will be important if they become long-range impactors?
All right. Hi, Kelly. Oh, that's a great question. I like to the way I like to answer that question is I am interested in these objects as a scientist, but it turns out that from a scientific point of view and from a hazard point of view, we're all interested in the same thing. I want to know their sizes, I want to know their shapes, I want to know their compositions, I want to know about their porosity. Those are all great science questions. So it's really interesting how the study that scientists want to achieve on these objects is the same that you would want to, same topics, the same measurements you'd want to address if you were dealing with a hazardous object. So there are size correlations that are related to surface porosity, the abundance of fine particles or regolith on the surface. The smallest ones tend to be more bare rock. They have a higher thermal inertia. And so that's not coming exactly out of the work I'm doing, but it's work that I have done in the past with Marco Delbo using the Keck telescope on Hawaii. We did an extensive survey of the thermal properties of these small objects. So there are characteristics in this population that in terms of their surface properties is related to their size. And the bottom line is the smaller you are, the more likely you're to be more like bare rock, mainly for the reason you have so low gravity you can't hang on to much debris.
Okay, that's it for the online. Okay.
Hi. My question's for Carrie. This is Nola Red, freelance. I want to follow up. I thought I understood from your presentation this morning when you were discussing this new cloud that it was that you thought it was part of a new cloud system, that there may be other kind of connected clouds. I just wanted to make sure I had understood that correctly, or you think it's just one isolated new cloud in the system?
Well, it definitely, okay. I mean, depends how you look at it, I suppose, but I was just trying to put it from a larger perspective. When you factor in the ISS cloud that was first discovered a few years back, so high up and so unexpected, and HCN ice was discovered to be one of the components of that composition. And then if you look as a system as a whole, chemically they're going to be different. And so they're not all the same component, but they're all sort of related because you have all these nitriles and hydrocarbons that will be subsiding and sinking as well, condensing out. But this cloud is new and it is separate. It is, it has its geometrically, its own once you do a deconvolution of the field of view and you get a geometrical thickness, it's about 30 kilometers in extent, and that's preliminary measurements I just did or retrieval I just did. And so it definitely is isolated. I mean, it's by itself, it's its own cloud located, residing at that altitude by itself. But I was just trying to put it, and even deeper down from that, which I didn't talk about today during my session, is that there's another cloud deeper in the stratosphere residing about 120 kilometers that is a different chemical composition. And throughout Titan's stratosphere, you have clouds just condensing because you subside and you cool and you condense. And that's kind of the story of the stratosphere in a subsiding region, which is what you get during wintertime. And so, but if you just look at a bigger picture, you can think of it like a cloud system, as you go into southern, winter, a bigger picture, but they're chemically different from each other. So they are isolated in that sense. But that's a good question, though. Thank you.
Emily Lochtawal again from the Planetary Society, and this is for probably both Carolyn and Rick. Getting back to the large dark objects that WISE keeps on finding, I found it rather alarming that WISE was turning up so many of these multi-100 meter objects so close to Earth. Should I have been surprised about that? And then how complete is the Neowise survey going to be for objects of this size in our neighborhood by the time the mission ends in 2017?
Go for it.
Sometimes we're also, surprised to see so many large dark things. But I would say that Neowise is very special in that it's, not blind to these very dark objects. And so you would expect it to find more of these big dark objects. As far as the completeness, I actually don't know the percentage. I know that we're not going to, with Neowise alone, reach the congressional mandate of finding the 140 meter bigger ones by the end of the decade. It's a hard problem to solve, and with the current technology, we're just not finding objects at a rate fast enough to reach that. Obviously, the lead into that is that Neocam would be able to find these objects at a much faster rate in the future.
Yeah, I'll take a crack at it. I think we knew we were incomplete, that we were lacking knowledge on the dark asteroid population. So it was an area that we knew we were ignorant, and that WISE would be highly informative. So it's hard to say we were surprised, but we knew we had a gap of knowledge there that's been wonderfully filled. With regard to the congressional mandate at 140 meters, WISE will find plenty of small objects at 140 meters and below. It's just then a question of completeness. The congressional mandate is to find 90% of all those objects. So WISE will find an abundance of them, but exactly, will it find 30% or 50%? It probably details that it may be in a proposal, or I'm not sure if they're public, but there's certainly a strategy that in the proposed mission there's a strategy to how to address the congressional mandate and at what level it will achieve. But I think it's a correct statement from my knowledge that it will not come up to the full 90% of 140 meter objects.
Okay, any more questions? All right, that will wrap it up, and tomorrow is our last series of press conferences here, so stay tuned at noon tomorrow. Thank you.